This is section 5-1. There's no homework in 5-1, but we're going to use these principles in the rest of chapter 5. So this is a review for people that need to have a review. This is a matrix. It's 3 by 3. The matrix has 3 rows. It has 3 columns. We have an element of the matrix. So the element is A11, and that means it's in the first row and it's in the first column. First row, first column. Matrices don't have to be, this is a square matrix. It has as many rows as it does columns. We say it's a 3 by 3 matrix. 3 rows, 3 columns. We could have a vector matrix. So this has 3 rows and 1 column. And the elements, first row, first column, second row, first column, third row, first column. And we could do that. We could take our matrices A and matrices B, and we could multiply them together. So we have A times B, and A is a 3 by 3 matrix, and V is a 3 by 1 matrix. Now, multiplication of matrices is only allowed if those two numbers are the same. So if I have a 3 by 4 matrix and I want to multiply it by a 2 by 1 matrix, that is not allowed. Not allowed. So it can only be done if the columns of the first matrix are equal to the rows of the second one. When I get done, I end up with a matrix that is 3 by 1. So the matrix here, this is all one element. That's one element. That's one element. So I have 1, 2, 3 rows, and I have 1 column. Okay, I can have a second matrix, 3 by 3. So I have a 3 by 3 matrix, which is A, and I have a 3 by 3 matrix that is B, and the 3's are the same. When I get done and I'm multiplying, I end up with a 3 by 3 matrix. So I look and I have a bunch of plus signs, but I don't have anything there, and I don't have anything here. So that's first column, second column, third column. I can add those matrices. So if I add a 3 by 3 matrix to a 3 by 3 matrix, then I end up with a 3 by 3 matrix. And in fact, I can only add matrices if these numbers are the same. So the 3 has to be the rows and the columns. I could have a 3 by 4 and a 4 by 3. That would be perfectly okay. 4 by 3 is. So they have to be the same in order for me to add them together, because when I get done, I'm going to have a 3 by 4. Well, I guess I blew that, didn't I? So they have to be the same, 3 by 4, 3 by 4. And if they're not the same, I can't add them. It won't be allowed. I can find the determinant of a matrix. So I have a determinant 1, 2, 3, 4, 5, 6. 1, 2, 3, 0, 1, 4, 1, 0, 8. That's all right. So I'm going to find that determinant. And so I'm going to multiply those guys together, get an 8. Multiply these guys together, get a 0. Multiply those guys together, get another 8. Then I'm going to go and multiply those guys together and get a 3. I'm going to multiply these guys together and get a 0. And I'm going to multiply those guys together and get another 0. 8 plus 8, 16, minus 3. So the determinant of that matrix is going to be 13. Another way I can do that is I can say I've got 1, 2, 3, we'll go 0, 0, 4, 1, 1, 2. We'll do that. I can go and rewrite the first two columns, and then I can go that way, go that way, go that way. Those are all added, and then I can come up this way, this way, this way. Those are subtracted, and I'd end up with my matrix. Now, if I had a bad day and I had a 4 by 4 matrix, well, we'll move back one. We'll move back to a 2 by 2. So I got a 2 by 2 matrix, 1, 2, 3, 4. And I want to find the determinant of that matrix. 4 times 1 is 4, minus 2 times 3, which is 6, which would be minus 2. So now I'm stuck and I have a 4 by 4 matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we're not gonna figure out what this guy is because that'd take too long. So I have something like that. 4 by 4 I can't do. So what I'm going to do is pick a row and I'm going to pick a row or a column and a column. So I'm going to pick this row. Boom, right there. I'm going to pick that row, and I'm going to say this guy is going to be minus 1 raised to the row and column of that 2. So that's row 2 plus column 1 times 2 times the determinant of everything that's left over after I take those guys out. 5, 9, 13, 7, 11, 15, 8, 12, 16. Plus minus 1, the row and column of that 6, so that's second row, second column, times 6, determinant of everything left over when I take those guys out. 1, 3, 4, 9, 11, 12, 13, 15, 16. Okay. Plus minus 1 raised to the row and column of that 10, second row, third column, minus all the things that are gone when I get rid of those guys. 1, 3, 4, 5, 7, 8, 13, 15, 16. Plus minus 1 times the row and column of the 14, second row, second row, fourth column, times 14, times what's left over after I've removed the column and the row that the 14 is in. And now we have methods to do 3 by 3. So we solve each of those 3 by 3s, and then we can solve the 4 by 4. The best I ever did was a 7 by 7. And of course it was on I needed a determinant. There were variables in it, so it wasn't like I could put it in my calculator and come up with an answer. And I had 35 pages of work, and because it was on a final exam, I had no idea if I got it right or not. I do know that I got a B in the class, so I must have done something. I also got a phone call the day before the test was turned in by one of the other students in the class wanting to know if they could copy off of me. And I said no and hung up the phone. I said I didn't figure it out and hung up the phone. I figured I had it wrong anyway, so it didn't really matter. Okay, now there are identity matrices, and an identity matrix are cute. They have ones going down the diagonal, zeros that replace else. And if I go A times the identity matrix of A, I get A back. Or if I go identity matrix times A, I get A back. Because that's the idea of identity. You should get back what you had before. So this particular identity matrix is 3 by 3. A 4 by 4 matrix would have ones going down the diagonal and zeros every place else. You're going to have to solve in the next several sections the determinant of A minus lambda I. So here's the determinant of A minus lambda I, and that's just one of those lovely things that you get to do. And what lambda turns out to be are eigenvalues. So you're trying to find the eigenvalues for the system of differential equations, and lambda gives you those eigenvalues. So you solve this, you set the determinant equal to 0, you solve for lambda, and in this particular case you'd have 3 of them because I have a 3 by 3 guy. So you'd end up with a lambda 1 and a lambda 2 and a lambda 3. And with a little bit of luck, there'll be enough zeros in the matrix so that it'd be relatively easy to get. If not, then your TI 89, 87, TI 86, TI 85, all solve for determinants of things like that. So you could enter it into one of them, and they would tell you what the eigenvalues are. Okay, that ends what we're going to talk about in section 5-1.